We wanted to record the talk.
Mm-hmm. All right.
Action.
We're good? Okay. All right, so talk is about monad transformers. I kind of anticipated what our audience would look like. A lot of you haven't had a chance to learn too much Haskell yet. That's fine. That helps me, actually, because I've spent a lot more time teaching the basics than I have the more intermediate or advanced bits of Haskell. So you're really just playing to my strengths. So this means that I'm actually going to spend a lot of this talk not talking about monad transformers or even monads. That'll come in the second half. I'm going to spend some time talking about functors and type classes so that we understand the basics before we move on to a more complex or stronger algebra. And that's going to be part of what you're going to learn. These are just algebras. So first off, functors. One thing to understand about a functor is its relationship to applicative and monad. I know you don't know what those are yet. That's fine. But anytime you have a monad, there's a functor in there somewhere. Monad is itself. You have a functor and actually an applicative functor before you have a monad. And we have to understand the weaker algebra before we can understand the stronger algebra. Okay, functor. So we implement functor in Haskell with type classes. You don't have to, but it's the most convenient way to do so. You define a type class definition with this syntax in Haskell. Class, that's how you define the class for just defining it. You're just defining the interface. If any of you have done like Java, it's kind of like that, but don't stretch the analogy too far. And then functor is the name of the type class. And then we have f, which is it's a type. In this case, it's a higher kind of type, and we'll learn what that is in a moment. And technically, functor has two methods. We're only going to concern ourselves with the v method, which is fmap. And its type is a to b. So this is a function argument right here. So we've got a function within a function here. And that function is being passed as an argument. And it goes from a to b to fa to fb. And then we also have a couple of laws. One is identity. If we fmap ID, it should be the same as if we passed our value to ID. Identity in Haskell is just a function that takes the value as passed and kicks it back out. So ID1 returns 1. ID, the string blah, returns blah.
I was putting my 1. That was 1. It returns 1.
Right. So the other is just, can we compose fmap? Can we compose two functions, f and g, fmap those composed functions, and get the same result if we composed the individual fmapped functions? And we should. And if it doesn't do that, it's a broken functor. Also, the identity law here, this is whenever you hear somebody, especially somebody with a more category theoretic mindset, if they talk about the structure preservation that functors guarantee, that's it right there. We shouldn't have messed with any of the outer structure that we're fmapping over by fmapping ID. That's why it's the same as ID. And I already went into some of this. I already talked about this being identity and about structure preservation. Without this, we can't compose things. We can't tease our code apart. Because this is about combining two functions and fmapping them all at once. This is about fmapping them independently. You're going to see what that looks like. In fact, I'll show you a quick example so that we can prove to ourselves that these things are true. So I have a REPL here. There's my fmap. The little, if you've used Ruby, you think that's a hash rocket. It's a type class constraint. It means that f has to implement functor. If you try to pass it a value that doesn't implement functor, it'll tell you done goofed. So fmap ID, who knows a functor? Give me a functor.
List.
Yep, list. Okay. What's going to happen if I pass that same list to just identity? Same result, right? Okay, that's identity. All right, what does it mean to have compositionality? We have +1 and times 2. And if I compose +1 and times 2 over 1, 2, 3, we get 4, 6, 8. But if I tease those apart, and instead I f-map them separately, I get the same result. That's the second law. I need to be able to do this with my functions, or I've lost all ability to compose and abstract my code. Absolutely mandatory. Otherwise, you don't have a functor. You have something that's functory-ish. Don't give it a functor type class if it doesn't satisfy the laws, because then you're lying to other people that ask for a functor. Okay. And I actually preempted myself here. I forgot what's in my own talk. All right, so, yeah, identity, composing. Okay, so what is fmap? Can I get anybody to suggest what they think f-functors are about? What they are? Essence? I'm not expecting a category theoretic answer.
Applying a function to data inside a container?
That's reasonable. Yeah, that's reasonable. So I usually shy away from the containery explanation. It's a good place to start, though. Now, the reason I shy away from the container explanation is that you'll think it's about, like, okay, what do we think containers are usually in programming languages? Lists, trees, things like that, right? Are functors useful for those? Absolutely. But that's not what a functor is. That's a subset. So the reason the container analogy isn't a bad idea, especially to start, is that you're talking about an A type argument to some F. So this F, in some sense, contains A. But it doesn't have to. And that's why you have to be careful with that intuition. But it's definitely a good place to start. And what we're doing is we're applying this function to the contents of our F and getting FB. Does that make sense to everybody? You apply a function that goes from A to B to the A inside the F, and then we end up with FB. Just textual substitution here. Just pretend you're playing games with text. Makes it much simpler. That's what people talk about when they're talking about like type Tetris or playing with the types. You're just playing with text. Okay, so this arrow here, it indicates a function. This is actually the type constructor for the function. So f is itself a type constructor that's taking a type argument A, but actually so is our little arrow guy here. So what this is indicating is a function that takes 2 arguments and returns 1 result. But the thing is that technically in Haskell, everything takes 1 argument. We're just nesting the lambdas to be able to accept multiple arguments. So the way this arrow works is it's right associative. So the parentheses associate from the right, which means that we can parenthesize it like this. So there's 2 different ways you can think about this. You can think about it in terms of application, which is what was hinted at with the container analogy. And what we mean by that is we're applying our A to B inside the F over the A and getting the FB. The other way to think about it is you're lifting it over structure. And that's what this parenthesization is intended to highlight. We're transforming our function. We're transforming our function A to B into a function that takes an FA and returns an FB. See the symmetry? Now, a couple different ways you put that is you're lifting A to B into the environment F, and that environment F is polymorphic because it's the functor type class, and it can be any functor you want. Another way to think about it is you're mapping A to B over F. Don't get too hung up on the words, though. What defines functor is the types and the laws. That's it. Any English word explanation, if it disagrees with the types of the laws, then the English word explanation is the thing that's wrong, not the types of the laws. Okay, so here's the list functor. All we did was we took our F, our FA and our FB, and we changed it to list of A, list of B. List type constructor has a little bit of special syntax to make it look kind of like a list or an array. That's why you have the brackets around the A and the B there. How do we implement the list functor? We're using this implementation on purpose. You will find out later why. But this is actually just map, right? It's just polymorphic map. Okay, the way we implement map here is with fold R. We're folding a list, and all we're doing is applying the function to the contents of the list, and we're composing that with consing, the result of having applied that function to the contents list, and we're folding it into a new result list. What that is like is it's as if you had this list, fold R, cons, and then we're going to do +1. Okay. That didn't break? Awesome. All right, so what's happening? This gets applied to 1, and that returns 2. And then that gets const. That's the const constructor to const something onto the head of the list. If you want to know what that looks like, it's like that. Okay, so then we're consing the result onto the list. You could think of it like this. If you wanted, that's not strictly accurate. Sure. Okay, so, but because it's in terms of cons, not the list syntax sugar, you're consing the results with the functions applied to them. So it would be more like, and so on and so forth. All right. And when we get an empty list, we return an empty list. Fold R is handling that for us. If we just defined fmap to map, it would handle that as well. You have to handle the empty list case. All right, another thing to notice here. In this fmap, we're going to talk about a list of A. That's going to be the type when we specialize the F to list. But in the type class definition, instance is how we define an instance of a type class for a particular type. The way type classes work are that you're supposed to have unique instances, a unique pairing of type class and type. So you shouldn't have multiple list functors. There should be one canonical list functor. There's several reasons for that. I won't go into them right now. But there's no A in there, is there? Can anybody tell me why? Why there's no A in here?
Because it's the type constructor that we want.
Right, exactly. If we look at our type here, our F has to be able to be applied to an argument A. That argument A being what we're mapping over. We don't have anything to map over if this is already fully applied. Because this is actually like a function at the type level that takes an argument, which is itself a type. It's a higher kinded type. When we want to talk about the structure of types, we talk about kinds. And we will go into that. Here's maybe. Same idea. We took F, we replaced it with the type constructor for maybe. Maybe is why we don't have null errors in Haskell, because we just replaced it with a simple sum type. Well, not too simple. It's still higher kinded. But the reason we want a higher kinded maybe type is so we don't have to re-implement it for int and string and all the other types in the universe. We parameterized it over A. So maybe can contain any A. Well, any type of, kind star. You can't contain a value type with the magic hash. But most of you aren't going to use that, so don't worry about it. Steven does, but most don't.
What?
A
what type?
So you're gonna see like the kind syntax in a few slides, but so kind star is the default kind for concrete types in Haskell. That an example of a kind star would be like int or string. String is actually just list of car, but it's still kind star because you took the list and applied it to the type argument car. Int is just a built-in type that represents a hardware integer. It's not a higher kind of type. Int is just a concrete type. It's also a pointer. It's a pointer to int. The default types are reference types that have pointers. So star is just a default reference type. The alternative is a value type. So you can have, like, as if in C you didn't have a pointer to an int, you just had an int. It's that idea. But there's kind of a line drawn in the sand between where you can have value types and reference types. You can't do certain higher level things. Also, reference types, they're actually the kind star. They're all pointers to value or thunk, actually. They're not necessarily a pointer to value, because otherwise it's not a lazy language, right? Whereas value types, no thunk. It's just the value. Okay, so maybe. That's why we don't have null type errors. We don't have to implement maybe over and over for every concrete type in the universe. Why? Because it's higher kinded, like list. The definition of maybe, we didn't include here, is this. This is how you define it. You could define your own if you wanted. It's not built in the compiler. It's not some one-off magic. You can write your own. That's the definition. So the first thing to notice, all right, this equals sign. Left-hand side, type constructor. Right-hand side, data constructor. This is what you use in your code. This is what you use in your type signatures. Type signature, code. Code, type signature. Now, it takes a type argument, A, right? Also, this A is not the same A here. They aren't syntactically significant outside of the expression they're used in. The letters have no meaning outside of the one, scope. Okay, we have a nullary constructor, nothing. It's just a value that stands for itself. It doesn't take any arguments, it doesn't do anything, it just equals itself. That's all it's there for. It's just there so you can pattern match on it. But then we also have this pipe here. What do we use pipes to represent in programming languages often? Or. Well, that's how we represent some types in Haskell. So it's kind of like in extended Backus-Nor grammar. If you've ever seen that, it's kind of like disjunction. It's the same idea. It's a sum type. It's saying when you have a maybe A, whatever that A might be, you have nothing or just A. Now, just is not a nullary constructor. It does contain something. It's a unary constructor. It contains one argument, one thing, and that's just A. So what you have to do whenever you have a maybe is you have to handle the fact, not manually, there's higher order functions, but you have to handle the fact and confront the fact that you may not have a value. So anywhere in Haskell code where we might have otherwise returned null, which doesn't exist for us, we'll actually just return maybe. So now you know in your types exactly where you might not get a result. You can just grep for maybe, and you'll see all your type signatures where you may not get a result. In practice, in more serious applications in Haskell, you won't use maybe that much. You'll end up using either for validation, something like that. Not terribly different though, same concept. Okay, so what type is that?
Maybe int.
Maybe, well, it's technically polymorphic, but yeah, no, it's okay. It's a morally correct answer. Well, the monomorphism restriction got turned off, so the literals are all polymorphic now. It can be any num you want. But I'm going to pretend they're int or integer. Unless I put like a dot and then, it starts looking kind of floaty. But anyway, yeah, it's maybe int. By declaring a just constructor with the type of value int, it can just infer the fact that it's maybe int. I don't have to tell it. The values are witness to their types, and that's how the type system knows what I'm talking about. And what type is that? Can anybody tell me what type that is?
Maybe A.
Right. And it's A because we don't know what our A is. We haven't given enough information to. So in Haskell, one of the nice things is that not only do we have polymorphism, but we have polymorphism by default. The inference algorithm will find the most polymorphic type that is correct. And the most polymorphic type that is correct for the nothing value is just maybe A, a rigidly polymorphic A. A could be anything in the universe, we do not know. In fact, as a silly example, I can actually assert an impossible type in here because there's no witness to the contrary in the value. Whoops. It doesn't want to show it, but yeah, here, we're doing getting down to the bottom thing again. Let me actually, yeah, there we go. So yeah, let that fly even though A to B doesn't exist. It actually does, I know, but don't use it. It technically exists, but technically, like in the type system, there's no such thing as an A to B. Can anybody tell me why A to B doesn't exist? In principle?
Because where do you get
B from.
Yeah, exactly. You don't know anything about A. There's no information there. It doesn't tell you anything. So you have no way to get from A to B. How would you? Incidentally, the function that you're not supposed to use that is A to B is unsafe coerce. It doesn't do anything. You're just casting the type. But that's why it's called unsafe coerce.
How's that any different from to string?
It's a different thing. To string's a coercion of string. That would be like show.
It's like.
Yeah, but you could have an A to string that just returns a constant string for all types.
Yeah, 'cause
Well, there's
you know
show.
what the, you know what the what's going that it's a string you're entering, whereas B.
If I have a function that ignores its argument and just returns a string over and over, I technically have polymorphic T to string, right? It's a trivial sort of function. It's technically correct, though. Why can it be polymorphic? Because I'm not doing anything with my argument. If I'm not doing it with my argument, it can be strictly any type in the universe. It doesn't matter. That's also why ID works for everything in the universe. Because it's not doing anything with its value. It can be any type. Because we're not expecting anything. We're not expecting any structure or type classes or anything. Okay, so, and just so you don't get the wrong impression, stuff with unsafe in the name actually don't get used and practiced in Haskell code. You don't have to worry about it. All right, so the implementation of functor for maybe. We're f-mapping f over maybe. F is our function. If we have just, we're pattern matching here, which is a way of dispatching on cases at the top level of the function. We just apply our f to the x inside, and then we rewrap it in just. Why do I rewrap it in just? What happens if I get rid of the just constructor? Is it going to type check? Why isn't it going to type check?
You're not returning a maybe value.
Right,
Or you're not returning a value that's still within.
Exactly. It has to stay maybe B. I can't implicitly maybe return maybe and then not return maybe. Doesn't work. Because I might not have anything. I can't guarantee I'm going to have a result. Maybe forces us to confront that possibility and not just, sweep it under the bed. Okay, so if I f-map increment over just 1, I get just 2. If I f-map increment over nothing, I get nothing. What does this save me? I don't have to case match every time I want to apply a function to something that's maybe, or list, or either, or validation, or const. There's a really long list of things that are functors, and I don't have to care about the specific details of those types in order to manipulate them. Functor lets me do that. So, kinds. Preempted myself again. Int, float, char, they're all kind star. They're just concrete types. But lists, little, brackets, they're kind star to star. They're a higher kind of type. They need an argument before they become a real type. Concrete types have values at runtime. These do not. Anything that isn't concrete, it doesn't exist at runtime. It only exists at compile time. This is important because that's how you know when you look at the definition of functor, when f gets applied to a, you can't be talking about an fa at runtime unless it was star. And what that tells you is it actually tells you how the kind inference in Haskell works. If there's only one argument left to apply to make it a concrete type, in the case of f applied to a single argument a, then we know that it's just star to star. It doesn't have to be. If it took 2 arguments, it would be star to star to star. So I shouldn't say all. We mostly use kinds. They're like, again, types about types in some sense, types one level up. We use them mostly to talk about the structure of type constructors, which is really just a way of saying how many arguments do they take before they become a concrete type. That's not the only use for them. There's also constraint kinds and other things. I will not teach you those here because they don't matter for our purposes. But if you want to learn about them, play ball. Okay, so Haskell has kind inference, unlike certain languages. You don't have to specify them. It can just figure it out from the definition of the type. You can query the kind in the REPL using the :k or :kind. Colon's how GHCI knows you're trying to talk to it and not write code. It's just a command, just like the :T thing I was doing with the types. All right, so first, trivial data type. Here's our type constructor. Remember, left-hand side, types. Right-hand side, values. All right, kind, trivial 0, star. Why is it concrete already? Because there's no arguments, and it just has a null array constructor. So it's already concrete. It's a trivial, type. It doesn't do anything. Well, it doesn't stand in for itself, but that's it. It's concrete already. All right, trivial 1, A. How many arguments does it take? 1. All right, so it has to take 1 argument before it becomes concrete. A single star.
But I think it's important to say that it's taking the argument on the type side, but not on the value side, right?
Right. Well, yeah. So you can have witnesses to like inhabitants of that type that don't take any extra arguments, like nothing and maybe. So it is strictly speaking at the type level. That's actually one thing these constructors highlight, is that it's not a real type until we apply A and B, but we never actually use A and B. Where's A and B in here? They're phantom. They're what's called phantom types. We actually have a use for phantom types in Haskell. We use them for like a primitive form of type indexing. There's more advanced ways to do that, such as with generalized algebraic data types and type families. Also not going to go into that today. Sorry.
So just so I'm clear, you can do that in the same REPL session. In other words, you can have trivial be.
This is me copy and pasting from GCI. The REPL is not like some stripped down version of GHC. As far as I know, there's like, Steven, is there anything the REPL can't do that you can do with the compiler that isn't strictly related to compilation? Because I know it's an interpreter, right? But like, I don't think there's anything.
So if you just type in trivial.
Sorry, hold on. I'd like to hear Steven. What? No? Okay. Yeah?
So if you just type in trivial, if you just type in :T trivial, what are you going to get?
:T trivial?
Yeah.
It'll say trivial 2, AB. You remember how nothing was maybe A? Our AB will be polymorphic here as well.
I think he's just asking, you're reusing the word trivial.
Right, yes. That's exactly
Oh,
what
I see. I'm sorry. Yeah, it just gets shadowed. We don't have overloaded record fields yet. We will in the next version of the compiler. And it will basically turn the constructors that overlap in name into basically an interface, a type class. And they'll become polymorphic. Whether or not you think that's a good idea, you missed it. Mailing list debate already happened. It's coming. It's kind of bringing us halfway to row polymorphism. I have no opinions on it. I mean, it's a pragma, right? So if I don't want it, I don't turn it on. If I want conflicting record accessor names to throw a warning or error, then I just don't turn on the pragma. And if other people want to use it, that's their problem. I'm going to play with it, and I'll make a decision then. But yeah, so in the REPL, yeah, you're just shadowing. It's just introducing a scope and shadowing what was previously there.
Connect the dots for me. Why did we start talking about records when we were talking about constructors here?
Well, because so this is just like a null array constructor.
Sure.
But whenever anybody talks about like overlapping constructors, they're often talking about record accessors more than they are actual constructors.
Okay.
So it just, yeah.
Same discussion.
Yeah,
Okay.
it's just kind of the same topic,
Okay.
like overlapping, yeah. Because usually it's record accessors that overlap, not normal like null array constructors. Because you'll have like, name, right? How many records are going to have name? I actually prefer to just prefix them and say like what it is, but some people really like brevity. I don't know. If you've looked at Bloodhound, you know I don't care that much about brevity. Okay, so kinds of day-to-day types we actually use, not trivial, which just, we're just slapping phantom type arguments onto it that we never actually use. Not that it would be that interesting if we did, but anyway. All right, so the bracket syntax for list, this is how it's defined in base, if I remember right. But it's special syntax. If you're going to re-implement list yourself, which you can do, again, not special, written in the language. Haskell is bootstrapped the same way lists and schemes are. No magic. All right, so you could just write it like this. just give it names. You could use an infix cons if you wanted, but I didn't here. Okay, so list takes one argument A. What is list? It's nil or a cons cell. What is it a sum of? It's a sum of a null array constructor and a product. Cons is a product. It's, you can think of it as a record. It's not really properly a record because we're not defining it so. It's just a product. We're not giving names to the individual fields. And what does a cons cell contain? A value and what? Rest of the list. Head, tail, car, catter. This is equivalent to a linked list. Pointer to value, pointer to rest of list, until you reach the end of the list. Okay, that is kind star to star, because you need to apply one argument, A, before it becomes a specific type. Maybe A, nothing, or just A. I already showed you that. Same deal, one argument, star to star. Either A, B, two arguments. Why are there two arguments? Because left and right can be different types. Are they required to be different types? You know the trap. They are not required to be different. They are simply allowed to be different. You could have an either string if you wanted. Don't do that. But you could. It would be silly, but you could. Also, incidentally, the two tuple is in some sense an anonymous product. Either is kind of the anonymous sum, because you can encode every sum in the universe just by having two sides to the sum. You can encode every product in the universe just by having two sides to the tuple. That could be homework if you want to prove that to yourself. But you can just nest them. That's why. You can just nest. Okay, so the kind of either is star to star to star, because it takes two arguments. First type argument, second type argument, then we're concrete. Functor and its kind. Functor is kind star to star, or rather our F that functor talks about needs to be kind star to star, because it gets applied to one argument. It can't be any other kind, because A, it needs to have an argument to be applied to begin with, and it can't have any extra arguments remaining to be applied, because we can't talk about something that isn't star at runtime in our actual code that executes. And that's how the kind inference is able to figure out, hey, F is star to star. I don't have to say so. Just figure it out. For functor, that's kind of trivial. When you start writing something cleverer than that, kind inference becomes kind of nice. I think mu would be a good way to demonstrate that. It's not immediately obvious what the kinds of things in mu are. I'm not going to cover mu either, sorry. Steven knows what I'm talking about, though. Okay, so, all right. I defined fmap to undefined, aka the almighty bottom, which apparently terrifies some people. I actually really like it, because I use it for sketching out code I don't actually want to write yet. Basically, bottom will pass as any type in the universe, and it'll just say it's correct. The type system just go, yep, all right, looks good. No type checking. Why? Because I don't actually care what the implementation of either is right now. Why? Because I'm actually going to ask you about kinds right now. I'm going to talk about higher level stuff. Then we'll talk about the implementation. All right, is this going to work? I'm going to outsource my type checking. We're not going to ask the computer, we're going to ask humans. Is this going to work?
Yeah.
Okay, anybody want to tell me why?
Your kinds. All right.
That's right. There's a kind mismatch. There's our kind mismatch. It wanted star to star, but either is star to star to star. Okay, but if you've written any Haskell, you know there is a functor for either. So how can this be true? How can we have a functor for either if there's a kind mismatch? What did I say these were? These are type constructors. They're like functions at the type level. What is the one thing you can, well, for my purposes, what is the one thing you can do with a function?
Partially applied.
Yeah, you can partially apply. Just apply an argument. The distinction between apply and partially apply in Haskell is kind of, it's all kind of the same thing. But yeah, you just apply an argument. Because if you apply an argument, what are you going to get? You're going to get star star, right?
Actually, so I'll ask the question because how do you apply to the second argument instead of the first one?
You're getting ahead.
Oh, you're going to cover this in your slides?
Oh, yes.
Okay, good. Yeah.
Oh, yes. This is like a pivotal point, yes.
I know a little bit of Haskell, but I haven't looked that up yet.
Okay. So, we already covered this. We're going to apply it. Also, the order of type variables will become important when after you already understand functor, and then you go to understand contravariant, and you're going to say to yourself, what the hell is going on? And knowing this is going to help you out a lot. Okay, so we can't talk about a functor for either, but if we have either A, B, we can talk about a functor for either A. So we've partially applied, whatever, who cares? We've applied the A, right? Okay. How many, if I've applied A, how many arguments do we have left before we have a real type, a concrete?
Just one.
Just one, right. So that gives us a star to star. Now it's going to type check. Actually, it won't because it'll complain about your either conflicting with the existing one in prelude, but if you turn on no implicit prelude, then it'll type check. But that's irrelevant. That's not germane. Okay, so ordinarily, either maps over, as in this is when we actually apply our function f. Normally, fmap maps over the right, not the left. We're going to find out why. All right. So I don't want it to. Let's say I'm a left-handed person. I'm not actually, but let's say I am. And in my protest of prejudice against left-handed people, I'm going to make a functor for either that maps over the left side. Why can't the left be the default, right? Why do we have to resume twice the right? Okay, so my instance of functors for either A, because I can't talk about a functor for either. That doesn't even real. Doesn't exist. Not a thing. But there is a functor for either A. Right? Okay. And then I'm just going to implement it. In the right case, I ignore the function, and I kick the same value back out. Basically, identity. And in the case where I have left, I'm going to take my f, and it's going to look a lot like maybe here. I just apply the f to the contents of the data type, and then I reconstruct the left value, because it has to stay in either. Okay. Is that going to work? We'll even take, let's take a vote. All right, raise your hand if you think that's going to work. Oh, man.
Wait, what?
Y'all are on the game here. You think it's going to work?
Well, I haven't looked at it too much.
Okay.
Sure,
All right.
Looks good.
Raise your hand if you think it's not going to work. Okay, the people that know me better. Yeah, it's not going to work. All right. What does a type error mean? What does it mean? Couldn't match expected type A with actual type B. All right, why did you expect type A? Because we were mapping over left A. But the actual type wasn't A. It was B. Can anybody tell me why the actual type was B?
Because that's what the constructing of the type of the concrete type put in, or it's the next argument.
From different scopes, right? We can go back.
So you're both like converging. I'm just gonna, I had a slide ready for this. Okay, so I was prepared. All right, so my f, we talk about an FA. If I'm talking about an A inside of f that we're mapping our function over, and we have either A, B, remember the A in here and the B in here is not the same as that in the definition of either. These type variables are independent of each other. So that's the first thing to realize. I could have made that more obvious with different type variables, but you're going to just have to get used to the fact that everybody uses A and B all over the place. Like you're going to see A, B, S, T, F, M, W. You're going to see a lot of those. Who can tell me what W is? What do we use W for?
Right, something.
No, comonad.
Okay.
Yeah,
That makes sense.
because it's a dual monad, so it's upside down with M. Yeah, I know.
It's like Mario with Mario.
Yeah, it is actually. Yeah. So, okay. So, you had the right idea, and you had the right idea, so let's merge them together. All right? When we applied A in either AB, the A is out of scope. It cannot be addressed by the type class. What is left after we apply A? What's left? Either AB, left A, right B. What's left if I apply A out of scope? The B and the right. Right? Just meaning the same words
I
here.
think it would be instructive to write out the signature of fmap when F gets specialized to either A.
Yeah. It's
Just like literally writing it out. So it would be like fmap of type takes a function A to B, arrow.
yeah, I know what you
And then
mean.
replace the F with the either A, and you might have to name
Okay,
it
so we
prime,
have
just,
A to B. So one thing that's going to make this a little awkward is the type variables. So I'm going to change this to C to D.
You can do A and A prime. I think that would work.
A and A, well, so if I use A here, they could mistake it for the A that we applied out, right?
Well, if you're just whatever.
Let's do B to B prime. Yeah, B to B prime. Okay. And then we go to, all right, what's our F? Our F is what? Either A, right? That's our F, but we need to talk about FA. So in that case, we actually mean B. And then we end up with either A, B prime. So we're not allowed to touch or talk about the A in either AB because it's not in scope here. It's hidden in the F. It's not being addressed by the type class. We can't talk about it. Not a thing. Just not there. So our F is either A, not either. And our A in FA is actually the B in either AB because the A got applied out. So how do we make this work? This type checks. My left biased either, it works now. Now's your time to shine. What did I change? Sukin? The left works now.
Oh, I see what you did. You flipped it
Flip to B and
leftably.
A.
Got it.
Yeah, I just flipped B and A. That's all. Boom. Left biased either. Now lefties can conquer the world. Right? Begins here. All right, so don't tell the government. All right, so now it works. And just real quick, this worked because now we're applying the B out of scope, and now we can talk about
This
the
is a little
A.
bit of a different solution than what I was really asking. Because, like, let's say that you have a data type that's already. Oh, are you going into that? Okay, sorry.
We're not. We haven't even gotten to monads yet.
Table. I'll table it.
Yeah, we haven't even gotten to monads
Very
yet.
good.
This is ostensibly about monad transformers, and we have addressed neither of those words. Okay, so let's talk about functions and their type constructor in kinds. A to B. It's an infixed type constructor. It's, in between the two type variables. It's the same kind as either because it takes the same number of arguments. Letters still don't matter. By convention, A to B. All right, it's kind star to star to star. There is no functor for function by itself. But what can we do with it to make it star to star? We can partially apply the type. And that's what we do. We take the function type constructor, and we have to parenthesize it like this because it's infix. Basically, we're making it like a prefix constructor when we do that. It's just syntax. And then we partially apply A. The first argument in the function type is the argument type, actually. So when we partially apply the function type constructor, we're making that go away. We're taking that out of scope for the functor. So the functor must necessarily be mapping over what? If we're talking about functions, and we took the argument out of scope, what are we transforming with the functor? What's the other thing? Right. We're transforming the result. The implementation of functor for this type is just composition. It's just composition. That's it. what does the type for that look like? Well, it's actually a little bit hairy for new people. So bear with me here. Okay, so what's going to kill you here is that this is just a more polymorphic, more general version of that. That was crazy, right? Like, how could that be the case? That doesn't even make sense. Okay, let's find out why. And that is how it's implemented. I'm not, creating a fantasy land here. All right, so let's talk about how that can be the case. Well, the first problem we have is that it seems like this takes, a different number of arguments, right? But it doesn't. What did I say? Every function in Haskell takes one argument, returns one result. Everything. It's just a question of whether your result is more lambda stuff. More lambda stuff, more arguments. Okay, so because of the way the associativity for the type constructor for function works, we can parenthesize it like that. Now they're the same number of arguments to our human eyes, right? Okay. All right. So how do we jigger this around? Here's what's happening. What did I say got applied out of scope? What's in our f for function? We're partially applying the argument type, right? So we're not touching that, right? Now, I know this is alien for a lot of you, but just look at the text. Don't get too heady about it. Just look at the text. A gets left alone, right? See, we don't touch A. We don't change the argument type. We just change the result type. We're threading the application of this function into giving its result directly to that function, and that changes our result from B to C. So composition is actually post-composition, because we're composing the functions applied through the results. If you want pre-composition, you want a contravariant functor. And that gets into what Susan wants to talk about, which you're not going to do. Sorry. You want the type constructor op, by the way, OP. If you just look at contravariant, Edwards library, you'll see OP in there.
Okay.
And what it does is it just flips the arguments around for the function type. That's all it does. And then pre-composition for op is just you're transforming the arguments.
It's bad at taking these
Huh?
I'm just joking. I was completely fine. Keep on going.
All right. So does that make sense? That this is our f, that is our f. There's our function that we're mapping, and that, B to C to C. And how is it implemented? Well, we have another way we can implement it. So we could use the dot, but we can be a little more explicit here. We could say,
Do you ever find yourself rewriting the type variables just to see a little more clearly, use a crypto quotes game?
Yeah, all the time. We could do
I was going to suggest, in fmap signature there, you could rename mentally A to B.
Yeah.
So
Yeah.
rename A as B, rename B as C, and then it lines up a little better with the compose.
Mm-hmm. So, let me... Okay, so it's that. Okay, so that's where the extra argument came from that we weren't really talking about in the functor, kind of, is we're returning a lambda that takes an argument. So that argument is x. We don't know what x is. We don't care what x is. All we care about is that we're applying our g to x, and then we're applying the result of that to f. Just like piping, like Unix pipes. That's all it is. We're just threading results through transformations. All right, and that syntactic form of fmap for functions, That's going to be important later. Going to be really important. Okay, so weaker and stronger algebras. For our purposes, I'm just going to say that algebras are a set of operations. What is that set of operations? The operations are the methods in the type class. The type class itself is the set. It's ad hoc polymorphism. It's parameterized by what type you're talking about for that type class. And the most apparent way to demonstrate that would be something like, okay, so monoid is a type class. Mempty is just it's polymorphic, but it's a concrete value.
Never said it out loud. That's so fun.
Oh yeah, I say it all the time.
How do you pronounce that?
Mempty.
Mempty.
Yes.
Speaking of pronouncing, how do you pronounce the equals arrows thing?
Equals arrows thing?
Like there was the thing between
Constraint.
So monoid A, constraint A?
No, just requires monoid. Monoid constraint. That's so the hash.
Call it implies.
It's just I just say it requires monoid A, or A has to be a monoid. Another way you can think about it is it's actually like an extra function argument, because it's almost as if you're threading the type class implementation as a set of functions that you're carrying around and then applying, but it doesn't matter. That's another talk. All right, so what's mempty? Well, it depends. Whoops. Oh, it wants a monoid for the A inside of maybe. Anyway, point is, I'm too lazy to write the constraint. Okay, so mempty list of A, empty list. So we're dispatching our mempty on the fact that it's a list. The A doesn't matter because the mempty doesn't have a witness to A, so it doesn't matter. And in fact, monoid isn't actually about higher kind types, so it's monomorphic in that respect. Okay, so weaker and stronger algebras. All right, so I said every monad also implements applicative and functor. That means it's stronger, contains more operations. It's a superset. That makes it a stronger algebra. The set of operations is larger. All right, so what's the advantage and disadvantage? Well, with a weaker algebra, you can decompose what you need more, and more types can implement a weaker algebra. But you can do more with a stronger algebra. Often what you'll do in some cases, especially if you're Comet, you'll start with a stronger, more unified algebra, and then you start teasing stuff out and abstracting them into independent concepts. And then you end up with a type signature that's that long. But it works. Okay, so monad. It's not a semicolon. Not a semicolon. Nothing to do with semicolons at all. Nothing to do with imperative programming at all. Yes.
Is it a burrito?
No. Yeah.
Why are you skipping applicative right now?
It doesn't matter. No. It's a good question. I considered it, but I realized it didn't matter.
Okay.
It's important if you want to actually write Haskell. It's not important for understanding monad transformers. If that makes any sense. I will mention applicatives later.
Okay.
Like when I talk about what compose does and doesn't work with, applicative will come up. But
It's just
applicatives are kind of brain bendy for people, and I can't spare the time. But it's good that you brought it up. You should all learn applicatives.
in the next.
I'm just not going to teach you right now. What?
Because in the next version of GHC, if you want to implement,
Yeah.
you want to implement the monad, you have to implement applicative
Yeah, the applicative monad
and
proposal.
functor.
Which will be nice. Previously, so historically, you only had to implement functor to have a monad. They're jiggering things around so that the full sequence of functor to applicative to monad is being recognized. So now, if you want a monad, you don't just implement functor, you implement functor and applicative. That's all. It's going to happen in the next version of GHC. It'll break some people's code. But progress, right? Progress is good. Yes? Okay. All right, so monads, not a semicolon. Nothing to do with imperative programming. It is just that. It's that type class. All right, so I did change things a little bit from the way monad is defined in Haskell. Doesn't change the semantics, just the syntax. One is I called it bind. People still call it bind, but it's that. The caret equals. I didn't use that because it doesn't matter. Remembering the syntax is not the hard part. The hard part is thinking in terms of abstract algebras. That's what's alien. That's what you need help with. Okay, so the other reason I changed it is I flipped the arguments. Yeah, I know there's a flipped bind. I don't care. It still has like nonsense syntax. All right, so.
What was your reason for not including return?
I'm sorry?
What was your reason for not including
Return.
Return.
Doesn't matter for now.
Oh, okay.
Yeah. With monad transformers, the applicative part just doesn't like. Well, it will. I'll use return later, but it just like doesn't matter.
Oh no, that's cool.
Yeah.
It's just okay. Never mind. I think I understand what you're saying.
Yeah.
That's fine.
No, it's fine. It's fine. So yeah, so return in monad isn't actually unique to monad. It's actually pure from applicative, which then harkens back to what I just said about making monad be based on applicative instead of directly to functor. It's really simple. It's a little weird looking if you're not used to it, but you just go to A to MA. Well, what does that mean? All right. Well, if I have a number, I'm going to monomorphize this so it doesn't look weird. Okay, so if I return 1, all right. But what if it's that? Whoops. Okay, and then none. Yeah. So what it's returning or injecting the value into depends on the type class. And it should be able to use maybe again. Hopefully it won't sandbag on me. There we go. Okay. So
quick quiz. Think about, so does anyone know why return 1 when you just typed it without the type integer, just return to 1?
He's working in IO right there.
yeah, and when you print an IO value, you don't see a type constructor for IO, or sorry, a data constructor for IO, because there isn't one. It's an abstract data type. IO is actually really simple. Anyway, okay, so if I say it's list event, we just inject it into a list. If I say it's maybe int, we just pass our value to just. It's just a way to go from A to MA. You need it for things. You'll see. Okay, so one thing I'd like to highlight here. Let's do this side by side. All right, fmap, bind. We can tell the difference. What changed?
There's an F in the end of your functions.
Right there?
Yes.
Well, the end of the function or end of that function.
Excuse me, but there's an F.
Okay, so, and if any of you want to know what applicative is, just take this F and like move it like right there. That's it, that's applicative, you're done. Okay, so, what we did was, instead of A to B, we have an A to FB. What does that change? What does that change? All right, our A to B in functor, all it can do is just transform, return a new value based on, you know, the contents of whatever our FA is, right? But this gets to return more monadic structure. This actually gives us more power. We can do more things with this algebra. You will find out what those things are soon. Soon. All right, here's the thing though. Bind isn't strictly essential to monad, because bind is actually join composed with fmap. Because it looks a lot like fmap already, right? Looks really similar. I mean, it's mostly the same. Just have that F there. But if we just fmap instead of bind our A to FB over FA, what type would I get if I fmap that?
B.
Yep, we get FFB. We get an F inside of another F. But that's not what we want. We want an FB. One F. Well, fmap already exists in functor. right? So F mapping a monadic function isn't really specific to monads. What is? Join. Oh, I gotta import control monad first. There we go. All right, now we can squish it. However you want to think about it, doesn't matter. MMA to MA. And that's how we end up with FB instead of FFB. Ding, ding. Okay, let's monomorphize it so it looks a little less crazy. Look familiar? That is bind for the list monad. Concat for list is just join. Map for list is just fmap. So bind for list is actually just concat map. That's all it is.
That flat map is gone.
Yep.
Yes.
Same here. Except with a much better name.
All right, so monomorphize a couple here. Bind for list A to list of B instead of A to B. List of A, list of B. And for maybe, A to maybe B, maybe A, maybe B. Now what does this let us do? What can we do with this that we couldn't do with the functor? We can choose whether or not we want to return a result. We didn't have a choice with the functor. We have to go from A to B. Now we can return a maybe B, but then we'll just be nested. So what this does is it gives us choice. We can say, don't return anything, fmap. But I just fmapped it. That's not really quite as useful. But if I bind it, I get nothing. So now I can manipulate the structure that gets returned as I'm mapping my functions as I go. It's the production of nested structure. Incidentally, when you have a co in front of something, you have a dual. Monads produce nested structure. Co-monads collapse enclosing structure. It's the opposite. We'll figure it out later. All right. So, the implementation for list monad. Remember how I said I didn't define fmap to map? Does anything look familiar here? Why didn't I define fmap to map for the list functor? What symmetry was I trying to show you? Well, I only changed one thing, right? Instead of cons, I'm using concat. Well, concatenate, I should say. Concat's a different function. But I'm concatenating my results as I map the function over the list that I'm mapping over. The reason I'm concatenating them is that my f is producing more list. So, I take an x, I return x, x plus 1, x times 2. All right, now I can fmap that over a list, but now I have nested lists. It's not really what I wanted, but what if I bind it instead? Now it's one list. So, I'm giving more power to my monadic function. It gets to produce more structure. What is that structure? Whatever your monad is. It's polymorphic. Just whatever your monad is. Doesn't matter what it is. This is pretty useful. Because imagine you have like a tree an AST for an interpreter. Now you could just transform that tree, but what if you could produce more evaluatable terms as you transform the tree and then reduce them as you do so? That actually ends up capturing a lot of business logic patterns. You'd be surprised. Okay, so the instance of monad for maybe is just this function maybe with a default to nothing and then fa. All right, so that is slightly cheating, but he has a reason for it. So, oh yeah, I should tell you, I forgot to say this at the introduction. This talk is heavily based on Tony Morris's talk on monad transformers. Only really the first half is original. The second half is me mostly repeating what he said and wrote, which is starting now. Okay, so maybe. All right, there's the maybe function. What does it do? B, A to B, maybe A, B. Okay. So the reason we can use this to define our monad is that B doesn't have to be maybe, but our monadic function is producing some maybe structure. So then our default value for B, because what maybe is doing is it's a combinator for handling the nothing case, we just return nothing. To see what that looks like, you can just there you go. Bind for maybe.
So quick aside, actually can you go back to are people familiar with this idea of having functions that sort of encapsulate pattern matching? So the lowercase maybe is kind of like doing a pattern match and maybe, so maybe has two cases, right? Nothing and just. So the first argument B is what you do in the nothing case, and the second argument is when you have a just A.
So to explain what he's talking about, you would normally have to, so there's two constructors in maybe, just and nothing. You would normally have to create like two branches for each case and then specify what you're doing for each of them. But that like shoves your code starting, like off towards the side, and then now your code is somewhere at the end of the line, somewhere in Timbuktu. You're really mad, and that one Vim user who always complains about ED columns won't shut up. So if you don't want that to happen, you use higher order functions, combinators, things that abstract patterns away. What is the pattern? What pattern this is encapsulating is your nothing in maybe, it doesn't contain A. So really there's only one thing you could possibly be doing whenever you have a nothing value in your maybe, unless you're reacting to some kind of enclosing scope. But all the same, you can do that with maybe. So since that's the case, you can just put like your little default value for the nothing case here, and then the function that actually produces a result based on the contents of just A is here. And then you pass your actual value that it's going to process. You'll get a better sense of how this works in the actual monad transformer code. Oh yeah, okay, so we had a function functor. What about a function monad? All right, now you see why I showed you bind for function with slightly different syntax without using the little dot. All right, let me bring that up. All right, that was the functor for function. This is the monad for function. Line them up. What changed? What's different? We'll talk about what it actually does in a moment. I just want to know what's syntactically different between these two, the functor and the monad.
There's more X's.
There's more X's. Okay. Who is X getting passed to in the functor?
Just G.
Just G. All right. Who is X getting passed to in the monad?
G of X.
Well, it's getting passed to G of X and F of G of X. Yes. All right. So now we're passing it to both. We usually call this reader, which kind of hints at what it does. we're making a value available to all the functions. This was more about composition. This was more about context. But you should not mistake that for thinking monads are necessarily about context. Only some monads are. Some are not. It's an abstract algebra. It's pretty hard to describe it in like one English sentence without just pointing at the types and covering your mouth. All right, so reader is pretty neat. But that's pretty strange, right? Because if we look at the types for bind, like how do we get to that? Well, our type was A to FB, FA, FB. All right. So RF is the function type constructor partially applied. So its argument is out of scope, only its result is in scope. What's happening here is instead of returning a function that just passes on its result and gets transformed by the next function, we're returning a function that takes an extra argument. And that's how we go from A to B to A to FB. That's what changes it. Because our F here is this. That's our F. That's our G. And then that's our final result. So F and G, you're going to see the same X. F is going to get the result of applying G to X and X. G is only going to see X. It actually ends up being a really useful pattern. What might we use this for? What if you have a piece of data that you keep passing over and over? The same functions, over and over, over and over, over and over. Now, you could just use variance-based order of arguments. So the arguments that are the least variant, that change the least often, they go all the way to the left. And then the ones that change the most go all the way to the right. And then you can just partially apply it. But that only works if you've got like one function that you have to apply a bunch of things for. If you have to keep doing it for a bunch of functions, and you'd rather just be able to kind of say, yeah, give me this thing. A little bit of hand waving. You do it with reader.
Hey, Chris.
Yeah.
You're out of memory. Do you want to delete Angry Birds or just keep it?
Just pause it. Just stop recording. We'll have to rely on Aiden's copy. Okay. So, nesting data types. What if we have a list of maybe A? Can we bind that? We can. All right, so let's talk about the functor first. If we want a functor for a list of maybes, we just fmap twice. We literally just fmap.fmap. And to prove to you that I'm not lying, I will do that. So that, move it up there. Okay, so that's a list of maybe. All right, but this isn't going to work. Because I've only lifted over the list structure, I haven't lifted over the maybe structure yet. Or mapped over it. Whatever verb you want. You can say you fuzzied over it. It doesn't matter. All right, so I've only lifted over one layer of structure with that code. That's not going to work. Why? Because maybe A doesn't implement none. The answer here is not to implement none. By the way. Why, does anyone
do that?
No, but you
I've seen people implement num for string. As a joke. But it has been done, so don't do that. You can do it. Okay. Well, particularly if you just require num for the A and maybe, then it works just fine. It's just like pointless. Okay. All I had to do was fmap.fmap. I just composed my fmaps. Right? Worked great. Well, to my mind, I don't know.
What's the type signature of fmap.fmap?
Good question. A to B, FF1A, FF1B. There is a pattern here. As you compose your F maps, you're just lifting over more and more structure. This is really convenient. Because now I can just map my functions over a bunch of structure and not really care how it happens. I don't have to keep manually case matching and if checking and all this and that all over the place over the same data structures over and over. The concept of just mapping a function over a structure is already reified for me in the form of this algebra. I don't have to do a case match on maybe ever again, and I don't. I don't need to case match on maybe. I don't even need those. I don't need those constructors really. I do for constructing just, but that's really kind of incidental. You could use a smart constructor if you want, just a separate one. Okay. So I can compose my F maps. Well, it turns out you don't need to like do it, once off for each functor. You don't have to create a special implementation for list and maybe. Do I use anything specific to list or maybe here? Is anybody willing to go to bat on that one? Yeah, I think so. Okay. I don't use anything specific to maybe. So if I just let Haskell infer my type, it's just going to say, yeah, give me 2 functors, and I'll lift your F over those 2 functors, and I'll apply it to the value and kick out your final result. That's a slightly abbreviated type, a little bit of a lie, because I'm not talking about the functors. Normally there'd be a functor constraint there. Bear with me. I hope you can forgive me. Okay, so we can just do that. And it works fine. And it works fine for applicatives too. Okay, so we can actually reify this concept of composing things, composing structure with the composed data type. It has an F, a G, and an X, and it's F on top of G with X. What do you notice here? What does that look a lot like? It's a data type, but it looks a lot like the definition of fmap for function, composed. It's just type level composition. But the types themselves, those type constructors, they're just functions, right? So it's the same idea, just at the type level. All right, so if f and g are both functors, we also have a functor for compose fg. Another way to say this is that when compose contains 2 functors, it gives rise to another functor. So that fmap.fmap thing, you don't have to do that. You can let an instance for compose do it for you. And now you don't even have to remember that you nested the structure however many levels deep. You can just use compose, and it works.
This instance is provided like control or something like that?
Yeah, compose exists. Yeah, you can use it. I think it's data.functor.compose, but I could be wrong. Do you remember, Stephen? Is compose in data.functor.compose? Maybe not in Prelude, no, but it's in. I think it's in base. Yeah. Okay, so the composition of 2 arbitrary functors makes a new functor. Another way of saying that is that functors compose. That is a slightly loose way to put it, because you know we're going to get to a point where something's different for monads, right? Monads do compose, but all right. So we want to bind now. You can ignore that cutoff text, I'll just tell you. All right, so we want to use the monads for list and maybe. So now we're not talking about their functor instances anymore, we're talking about their monad instances. We want to use the monad stuff. We want more power, more magic. Okay, so I want to implement my bind for list and maybe. So I use bind here. We're good so far, because bind is polymorphic, right? Works for any monad. Cool. But when I get to the maybe, I have to actually use that maybe function. And I have to return nothing, which injects my nothing value into the outer monad. Otherwise, it's the same. Just, applies the F. Can we use this for any 2 monads? Can we use this definition for any two monads in the universe? Nope, because I'm using information specific to maybe. We called bind on the list, which was polymorphic, but then we destructured the maybe using that maybe specific higher order function. So, if we want to do the same thing for monad that we did for functor for compose, can we implement our bind? No, we can't. You are welcome to try. It is impossible. If it was possible, we wouldn't have monad transforms. But monads do compose just fine. So what do we mean? What we mean is that you can compose monads all you want, but you're not guaranteed to get another monad out of the result. Not in general. You need a little bit more specific information in each case. So it's a little bit inaccurate to say that monads don't compose. They do. You just don't get to keep the monad part. And that's what I just said. If you wanted to try to implement the function I just showed you, you would need that type. That's not inhabited, which is another way of saying it doesn't exist. There's no way to implement it. If you do, I look forward to your crank paper and archive. All right, so, but our bind for list and maybe, well, we can actually make the list part polymorphic, right? Just any monad f, because we just use bind, which isn't specific to list. So we can make that part polymorphic, the part enclosing the maybe. But then we still need specific information about the maybe itself that is inside of the f. Outer part, inner part, outer part, inner part. All right, so when we do this pattern, we make a transformer for maybe, called maybe t. What does the t mean?
Transformer.
Yes. All right, so whenever you see the name of a data type you've seen before, with a nice big fat capital T after it, you're looking at the transformer version. All right, what changed? What's different about this from regular maybe? Well, for one thing, it's actually a higher kind. More kinded. It takes 2 arguments instead of 1. So the transformer version is always going to take an extra type argument, which we're calling f. Letter doesn't matter, as usual. And that f is going to get wrapped around the monad that it's a transformer for. And then it just contains, in our case, just the vanilla maybe. Plain old maybe that we already know. And then we can write a monad for this.
The curly braces, that's, what does that mean?
This is record syntax.
Okay, that's too old.
No, it's fine. It's fine. So this is a, it's just like the one constructor, but it's record syntax. It's so you have a record accessor, and we use it down here. That's why it exists. By having a record accessor, it saves us the trouble of case matching or pattern matching, which then lets us just use it like a function, which then lets us write type code.
Last time I wrote Haskell, these didn't exist. Records didn't exist.
Oh yeah, they definitely didn't. I know when you're talking about, so yeah, no, they didn't. When you start looking at the practice. All right, so, but we're not going to talk about any of those today, thankfully. Okay, so, our maybe is not polymorphic, but the f wrapped around it is. This is still helpful, because it means that we don't have to implement this monad for every combination of maybe and some other monad. We can write it once for maybe, and it's still polymorphic on the other side. So we don't have to write a monad for maybe in list, and maybe in reader, and maybe in da-da-da-da-da-da. We write it once for maybe t, and then the f is polymorphic. And you'll notice the implementation is mostly identical to the bind that we've already been using for this. The difference is we have a return, maybe t, and then we wrap it in the maybe t. All right, so provides the construction of the monad for f of maybe. So the f is wrapped around the maybe. It combines the individual monads of maybe, then F in order. Why is it in that order? Because this maybe stuff happens before the bind on the list does. That happens first, that happens second. Transformer exists because the composition of monads without specific knowledge of at least one of them doesn't give rise to a monad in general. So you can't implement that double bind. But you can still try. But you won't succeed. All right. So let's use our monad transformer. Let's write some code. All right, so first, this is our monad transformer injected data. This is our data. And it's a list of maybe an integer. All right, how does that work? Well, the first type parameter is f, right? And f gets wrapped around maybe. That's why it's a list of maybe instead of maybe of list. So we have a list of maybe values, and then we just inject it into the maybe t constructor, because otherwise it's not that. And then the integer is what's inside the maybe. Okay, the f1 here, that is our monad transformer aware function. And our monad transformer aware function is taking an n, and it's returning a list with just n, if n less than 10, then just n times 50, else nothing. And then we're binding it, and then taking it out of the monad transformer. We're just using the record accessor to pull it out. Okay, so we had just 1, just 2, just 30, and we got as a result 6 values. So to start with, why is this 3 values and why is this 6? Who can tell me? How many values are in this? 2, 3, 2, 6. Concat map. We're producing 2 values for each 1 value, which means we're basically taking the number of elements in the list and multiplying by 2. Okay? Now, the first value is just n. I put that there so you know which value got mapped over first. Bound. Whatever. Just 1. Just 1. Just 2. Just 2. Just 30. Just 30. Right? All right, now, who can tell me why the second value in the result is just 50? What happened?
Well, it looks like you multiplied that first value by 50.
Mm-hmm. That's right. And it passed this if check, right? Yep. Why did this one...
As if I can explain why.
All right. That's good. Why is this one nothing?
30 is not less than 30.
Right. And that returns nothing. This gives us more power. Now we can take advantage of the list. Ooh. No.
Yeah, hit the button.
There we go. Good. All right, so we're able to take advantage of both monads at the same time. We're taking the fact that because we're operating in the list monad, we get the power of concat map, which means we can adjust the cardinality of our results and get them all flattened in a final result list. And we're taking the power of the maybe monad, which is the ability to return or not a result. We get to choose whether or not we want to return a result. So we get to take advantage of both.
So what happens if you have a nothing in that M1?
Well, it'll be like before. It'll just end up being a nothing in a short circuit. Same as before. I can show you...
Well, where does the short circuit go?
well, in the bind for maybe. You remember how you called the maybe function, and you remember how it just kicks out the default value for maybe?
Okay.
It'll just kick the same nothing back out.
So you have nothing twice in the output.
If you had a nothing value, yeah. Yeah, it'll just kick it out twice. That's a good question.
So nothing doesn't enter the square brackets, basically.
Uh,
On your maybe T there. So it doesn't run the square bracket code there with just n comma.
Let's stay in comma. Well, let's type it in. Here, do I have? All right, so you see how that kicks nothing back out? So what's happening is the bind. It's as if you just f-mapped and then concated. Now, if I just f-map it, and then I have nothing, it just short circuits.
Okay.
Okay, so we understand how we got these results so far. All right, reader and maybe. This is going to be a little more brain twisting. Bear with me. All right, so what is it a reader of?
Integers.
Yes. Very good. All right, so it's a reader of integer. So it's a reader around our maybe t. And then our final result is, it's embedded in this monad stack is string. All right, so the thing is that I said our m was our data and our f was our function. When you're talking about reader, they're all functions, right? This is a lambda. It's data, but it's a lambda too. All right, so first thing to help us understand this, what type is n? This n here.
Oh, that's an integer.
Yeah. Because this wouldn't make sense otherwise. This is a PHP. You can't say a string is less than 100.
Well,
Okay.
I cheated. I figured it out that way instead of looking
Figured
at
out
the
the way you
signature.
Oh, no, it's fine. It's fine.
Figured it out.
Process by elimination is perfectly okay. Okay, so what type is x? I mean, the types involved are all up here, right? So there's only so many choices. There's nothing hiding. Right.
It looks like it's still an integer.
Right. And what did we say the implementation of the monad for reader? What did it do? What did it do with x? It passed it to f and g. F and g. That was f, that's g. So we're binding this f over that g. And they're both going to get the same number. All right, so to start with, they both have a condition in which they return nothing. Our g will return nothing when the number is even. Not even. Sorry, not even. Not even. And when it's less than 100, it'll do something with it. If it's greater than 100, it'll return nothing. Okay. So this is our actual, final data here that we're mapping the bound functions over. We're using map here because this part isn't the monad. The monad is the constructed function here that we're then mapping. It constructs something that wants one more final argument. Okay, so our 3. All right, first things first, let's think about order of evaluation here. Based on the parentheses, which of these happened first or get evaluated first? I'm not talking about strictness or laziness, just, based on the definition. It was f, parentheses, g of x, x, right?
I think n2 goes first.
Conceptually, yes. According to laziness, it'll actually get forced by f, because it's outside in. No, it's fine. I said it was irrespective
You
of...
said ignore laziness.
Yeah, no. It's fine. I'm just throwing that out there. Okay, so... All right, so let's do it in that order. Let's do the inside-out order because it's going to be a little easier to think about for here. Okay, so our 3, it hits our g first. All right, so what's x?
It's odd.
Yeah, well, it's asking for the value. Yes, it is also odd. Yeah, 3. X is 3, and this is going to be false, so that's nothing, right? Well, that's just going to short circuit, so then that becomes nothing. Okay, our second value is the most interesting one. But before we go to the second value, we're actually going to skip to the third. We're going to talk about this third nothing here. Okay, so we're probably talking about that one, right? All right, so the 700. Why is the 700 nothing? Because it's not less than 100, right. So it'll fly through this part, but this part will return nothing, and then we end up with nothing. All right, so But we do have just, and then the string 440. How did 4 become that? Well, let's take it step by step. All right, what's x?
So x is 4.
X is 4. So that passes, right? That's going to be true. All right, so x is 4 times 10 is 40. So then show turns it into a string, so it becomes the string 40, and then it's just, so it's just the string 40. It would look like that. Okay? All right. Now, here's the tricky part. We have an n here. What's n?
4 plus is going to be 4 again.
Exactly. That trips some people up sometimes. It's, it's fair. All right, so n is still 4 because it's the same value broadcast across all functions, applied to all functions. All right, what's s though?
That one's just string.
The string 40.
Just string 40, yes.
Wait.
That matters because it's getting bound over it. And if it binds over it, that means it'll short circuit on nothing and kick it back out. Otherwise, we wouldn't have gotten these.
Is that true? Wasn't
Yeah, by the time you get to s, it's the string. It's not the just.
Is it? Well, yeah, it is because it's getting bound over it. Yes, you're right. Oh, damn it. Yeah, it's A to FB, so it's the A inside of the F, which is string. Thank you. Okay, yeah, so it's string. It's just string. And that's obvious because we're not doing anything to handle the maybe here, right? Like, that wouldn't make sense otherwise. And we wouldn't need to re-inject it into just. Now, we could F-map this over a maybe, but we're not getting a maybe value, so we don't need to do that. Thank you. Okay. I didn't mess that up last night. All right, so our n is 4. Our s is the string, not maybe string, 40. All right. So we're concatenating it. Strings in Haskell are just lists. No, you don't use them for high-performance text processing. They're just a pedagogical tool. Don't use them in applications. I will find you. All right, so, or at least don't complain on the mailing list about how slow your program is and then it's nothing but string. All right, so s is 40, n is 4. We know that if we show it, we get a string. And then we're concatenating the string 4 on top of 40. And then we're putting it in just, which gets us there. Because we concatenated the 4 in front of the 40. And we put it back in just. All right, so relationships between the transformer versions and the non-transformer versions. And I'm worried I messed up the reader one, but anyway. Yeah, I probably did. All right, whatever. All right, so maybe T, FA, is F wrapped around maybe A. Either T, FAB is F wrapped around either AB. State T is F wrapped around AS. So state monad. Okay, it has absolutely no relationship to normal state mutation that you're accustomed to in imperative languages. None at all. ST does, state does not. It's pure, completely pure. So what we do with state monad is we just tuple the result of our function with the state. And basically the tuple acts as a side channel. It lets it return a value independently of how it wants to manipulate the state. But when we say manipulate, we're being a little bit disingenuous because you're not actually mutating and manipulating it, and you're just returning a new state. So the act of binding over multiple functions that are in the state monad, they're returning their independent results, independent of the state, and they're returning new states. Now you can actually have a reverse state monad, so it can apply things in reverse so that it looks like your state's flowing backwards through time. Then you can compose both of those together and get control.monad.tardis, which is a time-traveling state monad that lets you go forwards and backwards. It's really fun. You should look at it. It's really slow, but it's really fun. Anyway, these all exist because the composition of monads are not guaranteed to give you a new monad. That's why you do this. Functor transformers, not a thing. Because we don't need them, right? We could just use compose on the data types and we get a functor for free. I don't mean free objects there. But we get a functor for free when we compose them, so we don't need to bother with transformers for that. Comonad transformers exist. Applicative transformers do not. Functor and applicative transformers, those algebras are weak enough that composition thereof gives rise to a new one without any hassle on your part. Comonad transformers, though, the Comonad algebra is similarly strong as the monad algebra, so it has the same limitation.
Can you go back to the previous slide? Yeah. I wasn't expecting this equivalence for state 2 because state is what S arrow A comma S comma A comma S comma Z, right? And so like the other ones have the structure that kind of mimic what like reader T it like mimics what reader kind of looks like, right?
Are you talking about the order of the arguments?
I feel like there's a S arrow missing or something. I don't know.
Well, we can look it up. It says it's online. There we go.
Yeah, with my cell provider, that's never a guarantee.
Gotcha. State TS identity. There's the state transformer function itself. S to AS is run state.
That's the definition of state two.
The definition, click on it. SMA, yeah, S to MAS.
That makes more sense.
Yep.
And the other
Good catch.
observation I'll make on that slide, which is kind of interesting, is for all the equivalences except for reader, the F is appearing on the outermost thing.
Yeah, I thought I
It's just
probably got.
interesting.
You know what's also that tripped me up because I wanted
Does
the
that have to do with
Actually, I think the reader one's right.
position?
It's just that the F is weird.
But it definitely tripped me up because I was like, I thought I could just infer what the reader was going to be, and then I was wrong, and I fought myself over it because I
Well, so
wanted to be right.
the F is like, so the F is just like more function, right? So it just gets nested, and that's why it looks like that. But I might have gotten it wrong because I got the state T one wrong anyway. So
You know what? I did. Yeah. Sorry.
no, let me see.
No,
No,
I just
you
didn't
definitely
follow
got
the
that right.
conversation.
It's just
Oh, yeah.
So a quick note: if you want to get from the transformer version to the regular version, you don't actually ordinarily do this. You can actually use identity to do it. The identity is kind of like a pass-through functor monad applicative. It doesn't really do anything. It's just a unary constructor that contains a thing. So it's just
the kind reduction.
sorry.
I mean, like you got this identity A. That's
Right, because it has to be higher kinded too.
yeah. It's kind of just throwing away that information.
No, it doesn't.
What are you trying to do?
The A's here.
I'm just trying to say it's a kind reduction. That's all.
I don't know what that means.
Or because you got it.
You kind of want to treat A's like monads, but is that what
No.
you're getting
I'm
at?
trying to get it as Yoda type, right? But you need it to be of a certain kind for it to be a functor. You might not be explaining that and stuff.
Identity's kind is compatible with functor and monad without partial application. Because it has identity A. So our A is just whatever's inside the identity. Yeah, it's nothing special. So the reason that's important is that it basically makes the enclosing monad do nothing. And if it does nothing, then, it's as if you just have maybe A, right? That's all. And that's the last slide. Okay, so a few things I didn't cover that could possibly become rather important should you want to write Haskell applications. One is lift. Some people hate it. Some people think it's absolutely critical. But it's be best off just bringing up.
Lift the function.
Yeah, from transforms.
I don't know all these.
Haskell.
Yeah, so, okay, lift, monad M, MA to TMA. It's a way to lift it through your monad stack. An example would be like, if you're inside, say, you're writing a Scotty web application, and you're inside Scotty's monad. Scotty's monad doesn't, it's not I.O., right? But you have a function that talks about I.O., but doesn't talk about Scotty. You can lift it over that structure using lift. Or actually, in this case, you'd use lift I.O., I'm sorry. For I.O. specifically, you'd use lift I.O. And an example of that.
People hate lift. That's the other side of the argument.
Oh, yeah, so you're thinking of Edward Yang's
No, I
blog
not
post?
think about anything. You just made the comment.
Oh, yeah. Some people think you should try to avoid it because it's like a sign that you're forcing yourself to care about like how your monads are ordered and stacked up.
Mm-hmm.
That's where you get into like MTL style monad transformers, where you have a type class for each monad in your stack, and then you don't need to worry about the order. It just kind of zooms to the monad, and then the rest of your stack becomes polymorphic, and you don't worry about the rest of it. And that basically makes your code less likely to churn and break because you reordered your monad stack or something.
Okay.
Yeah. Whereas if you lift through each layer manually, it's like lift IO zooms to like IO, and then like the MTL stuff, like tell and ask for like writer and reader and state and all that, they let you just zoom to whatever that is in the stack, which is qualitatively different from knowing that your reader is like 3 levels up and then you lift 3 times. Right,
So
like
if
that's
you didn't
different.
have lift.io, you'd be like lift, compose, and like compose with itself a couple times.
Yeah, I think so. Stephen would know more. But does that sound right?
If you write your monad transformers in the MTL side, you should have that.
Oh, okay.
Is that
So
what you prefer? To have a button or a preference?
Except when you have IO,
you end up using transformers or MTL. So MTL and transformers used to be the same library. They got split out. They got split out because MTL relies on a pragma that not everybody's jazzed about. Not everybody likes the pattern. How useful MTL is to you depends on how much like reader, writer, and state monad you're using. If you're using them all over the place or they're somehow integral to your application, yeah, save you some hassle. Otherwise, the basic transformer stuff is probably fine, if only for lift and lift.io.
The transformer builds off MTL, am I right about that?
I think.
Other way around.
MTL builds off the transformers.
Okay, good.
And the other thing about MTL is like even if you don't plan to use it, a lot of libraries do. So it's worth understanding. There's a paper for MTL that explains why they're using functional dependencies and how it works. I am not equipped to relate that to you. I still haven't read the paper. But it's in the queue. And I'm done. I'm tired.
Awesome, thank you.
The only thing I was going to add, in case anyone had the passing idea, like